Early in the morning on December 14, 2005, a massive wall of water, 1 billion gallons, suddenly came rushing down the slope at a terrifying speed, destroying everything in its path. Trees, trails, even the house where a family was peacefully sleeping, all of it was swept away by the wave of water. It's been almost 20 years, but the road the channel made is still clearly visible. Nothing has grown here yet. But the most interesting thing is that all this water on the mountain wasn't supposed to be here at all. It was pumped up by people. And the idea was, of course, pretty good. Bring water up to the top But let's take it one thing at a time. And first, coffee. Just an unobtrusive reminder to do something under the video. And thanks. You know what for. So what exactly are we talking about here? This is the Sauk pumped storage plant located in St. Francois Mountain region of Missouri, USA. It was built between 1960 and 1962 and went into operation in 1963. So it can generally be considered a relatively modern facility. Once construction was finished, the power plant became the largest pumped storage hydroelectric facility in North America by several criteria, marking a significant milestone in the development of the technology. In other words, it was an incredibly advanced and cutting-edge project for its time. The Sauk pump turbines were the largest ever produced in the U.S. at the time. The plant also featured an exceptionally high head and the largest storage capacity in the country. It was also capable of being restarted even after a full blackout and could be operated remotely by human operators at external facilities. These facilities were located at a distance of up to 124 miles away, but it was also possible to leave the station to itself, fully automating all processes. Can you imagine how awesome and fresh this was in the 60s? And everything, basically, was working the way it was supposed to until one of the station operators made a prediction. Here's the letter he wrote to his supervisors on September 27, 2005. Overflowing of the upper reservoir is obviously an absolute no-no. The dam would severely erode and cause eventual failure of the dam. If water continued to spill over the top of the wall, it could cause a section to collapse, and then it would be all downhill from there, literally. And exactly what he said would happen, happened. But in order to figure out what went down, we need to understand what this building was, how it was built, and why it was created. Let's start with the fact that the Sauk was built as a pumped storage hydroelectric plant. In one of my recent videos, I already explained how they work in detail, but for those who missed it or have forgotten, let me quickly go over it again. Any pumped storage power plant's basically a giant battery, and it doesn't produce its own electricity at all. Instead of generating energy like a coal or nuclear plant, a pumped storage plant stores it when the demand for electricity is low and releases it during peak hours. Because managing the power grid isn't just about how much electricity you can produce, but also when you can produce it. Big coal plants in the Missouri area where Sauk is located could generate a lot of power, but they couldn't ramp it up quickly enough to meet the changing demand throughout the day. But the new plant could. The energy storage happens when water is pumped from the lower reservoir to the upper one, and of course this takes electricity. The release happens when water is let back down from the upper reservoir to the lower one. The turbines that the water flows through at this point generate electricity. It's true that it takes more energy to pump water up a mountain than you get back when it comes down. Still, the power plant's economical to run because the upper reservoir is refilled at night, which, to put it simply, is cheaper than doing it during the day. Overall, these batteries are really effective, even with the loss of some water and electricity, and of course they exist all around the world. This is what the Fengning Pumped Storage Power Station looks like, built in China. And this is one in the Bath County Pump Storage Station located in Virginia, USA, and it's considered to be the world's largest battery. Here's another station, also from China. All three work exactly the same way as the Sauk station we're talking about today, but they're built in completely different ways. Take a good look at the upper reservoir. It's completely different from other similar structures because it was made entirely by human hands. Essentially, it's a circular dam in the shape of a beam built on top of a mountain. Usually, this method of building a dam is considered inefficient. Most often, people use natural valleys as upper reservoirs, and then the natural terrain, mountains and rocks, become the walls of the reservoir. All that's left for a person to do is build a dam across the valley to keep the water inside. Obviously, this is much more cost-effective. Why build 10 walls when you can settle for just one? It sounds pretty reasonable, but finding the right place could be hard, really hard. First of all, the station should be located in the mountains because its basic principle is the difference in height between two reservoirs. Without that difference, there won't be any electricity generation. Secondly, the station should be located in a convenient spot for the company so the electricity it generates can be delivered to the grid in the most efficient way. The chosen final spot, the 6th highest mountain in Missouri, offers a nice elevation change of 755 feet and is just 27 miles away from the existing network. And although pump storage plants can be found all around the world, the Sauk station is unique because water is pumped into the upper reservoir. In most other stations, the natural primary flow is used for generation. But the reservoir has other peculiarities too. When it was being built, the material that was dug up was used to form the dam. Essentially, it's just a long mound of stones that was piled around the reservoir's perimeter. And as strange as it sounds, a stone embankment usually works pretty well as the primary material for a dam if you have a good source of material nearby. It's really sturdy, doesn't need much compaction, and doesn't sink much over time. The only thing a stone embankment doesn't handle well is holding water. There's just too much space between the rocks. That's why concrete slabs were installed all along the inner side of the reservoir. They made the embankment watertight. A tunnel was drilled through the mountain from the reservoir, linking the whole setup to the power station. The inlet was placed in a pool 20 feet below the bottom of the reservoir to prevent vortices from forming during daily water discharge. As I mentioned, the entire project was designed to be run remotely without bringing in local experts. A cutting-edge idea back then, and it's one of many choices that ended in disaster. Before the big overflow happened, the one whose effects we're still seeing today, there was a smaller one. You could call it a trial version of the disaster. On September 25, 2005, a few company reps visited the upper reservoir and suddenly noticed water spilling over one edge of the dam. Witnesses said it looked like a mini Niagara Falls. The system operators quickly tried to shut off the pumps manually and adjust the water level to stop the flooding, and, well, they managed to do it. Right after that incident, just 2 days later, the email I mentioned at the beginning of the video was written. During a minor overflow, the operators quickly switched from pumping to generating mode to send the water back. They blamed the issue on strong winds left over from a recent hurricane, which supposedly caused the spillover. The wind was real, no doubt. On September 25th, Hurricane Rita stirred up some waves, causing a slight rise in the water level of the upper reservoir. But as it turned out, the hurricane wasn't the culprit. The later disastrous overflow came from entirely different reasons. For most of its history, the Sauk station ran about 100 days a year on average, typically during the hot summer months when daytime and nighttime electricity demand differed sharply. Then came the 1990s, bringing the opportunity to sell power to other utilities, and those 100 days a year turned into 300. This meant the upper reservoir was filled and drained often twice a day, nearly every day of the year. And that started to cause some problems. Leaks through the floor, walls, and valve seals of the reservoir started popping up practically from day one, and heavy use only made things worse. You can see on the graph that it got really bad after 1999. The solution to the problem was to line the inner surface of the tank with a special geomembrane. The graph shows this too. Once the membrane was put in, the number of leaks definitely dropped. The only thing is, new issues started popping up. Since the initial design didn't include a drainage system, the dam was equipped with 2 drive systems to stop the 2 pumps at the site if the water level in the reservoir exceeds the desired level. In 2004, when the geomembrane was installed, the pump shutdown mechanisms were also updated. The new system consisted of 3 pressure sensors and high-density polyethylene pipes secured to the concrete layer to trigger a shutdown when necessary. Basically, the engineers installed sensors that were supposed to track how much water was in the tank and shut off the pumps if it got too high. And the problem was in these sensors. Later, when divers investigated the possible cause of the first mini spill, they found that several pipes where sensors were installed had come loose from where they were originally fixed. As a result, the sensors' ability to report accurate water levels was compromised, and lower readings were recorded. This is what the sensors were supposed to look like to work properly. And this is what they looked like when it came time for the check. It seemed like the situation needed urgent fixing, but a full-blown repair had to be postponed. To make sure it didn't lead to disaster, some steps were taken. Spoiler, it didn't help, though people really tried. First, the system's programming was changed to report the water level in the tank as lower than the actual readings of the sensor. This was done to avoid false positives that the sensors were giving. Second, special probes were attached to the inner rim of the tank as backup sensors. They were supposed to automatically and completely shut off the pumping system if the water level in the tank reached their level. The worst part is that even though the company knew about these faulty sensors, they didn't fix them and didn't let anyone know they were broken. Because of that, by the way, the company later got fined $15 million. The company also estimated that these measures with the additional sensors would be enough to avoid issues until the full repair could be done. They've postponed it until the annual maintenance period when the tank is drained. Unfortunately, the dam didn't hold up until that time. On the morning of December 14, 2005, the northwest side of the upper reservoir overflowed. The water kept coming from the lower reservoir, and when the level at the top reached a critical mark, neither the sensors nor the probes could report it to shut off the pump. The water started overflowing on the northwest section of the dam at 5:09 a.m. The flow over the parapet was like the one over a broad crest weir, and at first it crashed onto a 3-foot outboard wall surrounding the dam. Everything happened just like during the incident in September, except this time there was no one nearby to see it and stop the process. According to some reports, the breach even happened in the same spot. Unfortunately, all the cool automation in the system turned out to be useless and even harmful. As the amount of water in the reservoir increased, the path of the draft shifted further away from the reservoir, eroding the exposed and unprotected stone embankment. The ongoing erosion of the embankment eventually caused the dam to break. And by the way, it was 650 feet wide. All the water from the reservoir gushed out. This led to the catastrophic failure of the triangular section of the dam wall and the release of those 1 billion gallons of water in just 25 minutes. A torrent raced down from Prophet Mountain to the Black River, hitting a peak discharge of 273,000 cubic feet per second. Before the flow stopped, nearly 280 acres of the Johnson Shut-In State Park were wiped out, and the manager's house was washed off its foundation. Damage estimates from the breach and the subsequent flooding reached up to $1 billion. It's a miracle that no one died from the spill. Jerry Toops, who manages Johnson Shut-Ins and Sauk State Parks, along with his wife and 3 kids who were in the house when the flood hit, were injured and suffered from cold, but survived. Feels like a miracle because this is all that's left of their house. The flood continued downstream to the dam, feeding the lower reservoir for the station. The lower reservoir dam, designed to hold most of the water from the upper reservoir, withstood the pressure of the flood. By holding back most of the flow, it protected the cities downstream, including Lesterville and Centerville, from the destructive flood. In these areas, a voluntary evacuation order was issued, but it soon became clear that it wasn't necessary. No damage was done. The park and the manager's house took the full brunt of the hit. After people recovered from the initial shock, an investigation followed, and this time it was really thorough. Experts concluded that the disaster was partially caused by poor design and issues with the instruments. Mostly they blamed the loss of stability, bad design, poor technical specifications, and maintenance of the instruments and control systems. The investigation also found that repairing the existing dam is technically impossible due to flaws in the original design. Large sections of the dam were built on residual soil. On top of that, there was very little construction supervision when the dam was first built. Remember I said that a stone embankment's great because it sinks less, right? Well, the rocky ground it was supposed to be made from turned out not to be as rocky as the engineers who designed it had thought. There was a lot more other soil mixed in, and as a result, the embankment started doing exactly what it wasn't supposed to do over time. It began to sink. The weak spots in the foundation weren't properly cleared, which made the sinking even worse. During construction, some parts of the parapet wall ended up 2 feet below where they were at the start. This sinking wasn't taken into account when the level sensors were replaced after the lining project in 2004. So because of that and a few other factors, a complete rebuild of the upper reservoir was necessary, this time properly. The reconstruction started almost 2 years after the overflow. Instead of the earth-fill dam, a new one was built using a stronger method of compacting with a roller, and now the engineers are concerned with adding a spillway in case of an emergency overflow of the reservoir. The dam cost $500 million. Luckily for the company, most of this amount was covered by insurance. About 6 million tons of rock from the original dam were used as filler for the new roller compacted concrete structure. This special mix is made of cement or fly ash, water, sand, aggregate, and regular additives. It contains much less water, so the mix is drier, and once it dries, there's almost no settling. Changing the technology led to minimal waste and eliminated the need to haul any materials off-site. 5 concrete plants, 4 of which produced the roller compacted mix, operated simultaneously and produced between 5.5 and 7 miles of concrete per day on average. On February 27, 2010, water was first pumped into the reconstructed reservoir, and for some time, engineers kept an eye on how the new structure reacted. As the water level went up and down repeatedly, the final approval from the Federal Energy Regulatory Commission to return to normal project operations was only granted on April 1, 2010. On April 21, 2010, electricity was first generated at the new structure. The updated dam was recognized with the Award of Excellence in the Constructed Project by the United States Society on Dams. Yes, it turns out there is such an organization as the United States Society on Dams. I was surprised too. A similar plant. Take a look at this artificial reservoir located above Lake Michigan. Does it remind you of anything? It's basically the twin of the Sauk pump storage power plant. Even the shape is similar. This huge reservoir here, just like the one at Sauk, not only stores a huge amount of water, but also helps generate electricity. Since its launch in 1973, the Ludington storage plant has functioned as a giant battery, continuing to operate even after half a century. The vast reservoir covers an area of 840 acres with a length of about 2.5 miles and a width of 1 mile. To protect the intake and outlet channels from the waves and currents of Lake Michigan, 2 breakwater dams and a barrier were built. From April to October, provided there's no ice, the structure is used to prevent fish from entering the station's system. So what's inside this storage station? The Ludington pump storage plant operates with 6 pump turbines. According to Consumers Energy, which owns part of the station, each unit can change the water level in the reservoir by 1 foot per hour during regular operation. At peak load, the facility can supply electricity to up to 1.7 million households. And although most of Michigan's electricity is produced by coal and nuclear power plants, it can't compare to a pump storage station, mainly because they can't store excess energy when demand for electricity drops. As you can imagine, such a large facility can't come cheap. Ludington Pump Storage Plant cost $327 million in the 20th century. With inflation, that's roughly equivalent to around $2.7 billion today. Yeah, it's a big amount. But the benefits of the plant, as usual, make the high cost worth it. Hydropower without water. Hydropower is something that definitely needs water to work. The very word implies it. With the help of water, a huge amount of energy is generated, it accumulates, blah, blah, blah. You've all heard that before. But even though there's been an increase in hydropower plants recently, there's a limit to how much they can grow because most of the good spots for them are already taken. So what's next? Well, for one, we could substitute water with something else. There are plenty of other liquids in the world, right? A company from the UK called Reconstruction has developed a unique method that can bypass the limitations of regular hydro storage systems. They proposed using a special solution that's 2.5 times denser than water. This solution's made by mixing water with a special mineral powder, which turns the mixture into a heavy, paste-like liquid. What's the advantage over water? Well, at least thanks to the increased density of this liquid, the energy storage efficiency becomes comparable to regular pumped storage plants while requiring 40% less volume. This allows for much more compact reservoirs or a 40% reduction in the height difference between the upper and lower pools. This way, the technology becomes available for regions with low hills. The company claims that over 6,500 suitable locations have been found in the UK for such installations. Reconstruction also claims that their solution is cheaper and safer compared to pumped storage hydropower. There's no risk of leaks like what happened at Sauk. This will allow energy to be stored for several hours, days, weeks, or even months depending on the region's needs. According to the company's plans, its first project will have a capacity of 10 megawatts, and then within 2 years, the installation will be integrated into the power grid. Highest pumped storage plant. In 2024, China began building the world's highest pump storage power station. It'll be located at 14,000 feet in Daofu County, Sichuan Province, and it's going to be truly amazing. The power station is set to have a capacity of 2.1 million kilowatts, which will allow it to generate up to 2.9 billion kilowatt hours of energy per year. As the largest pump storage power station in Sichuan, the new plant will be equipped with 6 reversible units, each with a capacity of 350,000 kilowatts. There, of course, will be reservoirs. Plans include both upper and lower ones. Project also includes a water transportation system, an underground power station, and a ground-level distribution point. With a maximum elevation difference between the reservoirs of 2,500 feet, this hydropower station will be second in China for head height among similar stations. Despite the grand scale of the project, China has no experience building structures at such a high altitude, so the station in Daofu promises to be challenging both in terms of design and in terms of producing electrical equipment. But if it all works out, the massive battery will store up to 12.6 million kilowatt hours of energy per day. That's enough to power 2 million homes. The new hydroelectric pump storage power plant will also be environmentally friendly, which is also very important in today's world. In short, no downsides, only upsides. Transforming the mind. Actually, building hydroelectric pump storage power plants seems to be a new trend. More and more countries are turning to this way of generating and storing energy, replacing traditional methods. For example, the Australian Renewable Energy Agency has approved up to $47 million for GenX to create a pump storage system. What's interesting is that the project will be implemented on the site of a former gold mining operation in northern Queensland. The new hydroelectric pump storage power plant will make use of an already functioning 50-megawatt solar power plant on site. Plus, they plan to build another eco-farm, this time a wind farm with a capacity of 150 megawatts. All of this will cost the company GenX $777 million, which is a lot. But at least the useless quarries will be turned into a massive battery. They closed back in 2001 and have been sitting there unused ever since. So why let something good go to waste? According to the plans, the power system will have a capacity of 250 megawatts and be able to store up to 2,000 megawatt hours of energy. That's enough to power about 143,000 households for 8 hours. It's some kind of amazing eco-combo: wind turbines, solar power, and water, and zero carbon emissions. Did you put something under the video? See you later.